Actually, you can start yours. Okay, so everybody, welcome back to the Symmetry Seminars. We're starting off the summer break, and it's a great pleasure of Andrea Antinucci from SISSA and at the assignment center at the moment, talk about anomalies of non-invertible self-duality symmetries. Take it away.
Hey, everybody. Thank you, Segura, for the introduction, and thank you, all the organizers, for inviting me to talk. This talk will be mostly based on this second paper here, which I wrote together with Francesco Benini, Cristian Covetti, Giovanni Galati, and Giovanni Rizzi. And I also want to mention this other paper, which came out together with ours, which discuss similar topics. And this is going to be about anomalies of non-invertible symmetries. And as you might know, this is a quite subtle topic. Indeed, these anomalies are also even hard to define. And I will not provide a definite answer to this complicated question. But in the first part of the talk, I would like to discuss several possibilities and try to motivate why I'm going to use a certain notion for these anomalies, which I will use in the second part of the talk. So let me start by making some quite simple remarks about more standard anomalies for invertible symmetries, which are typically defined by the fact that a certain quantum field theory with a global symmetry G, let's say an invertible symmetry, when you couple it to a background gauge field for the symmetry, the partition function could be not really invariant under background gauge field transformation, but can be invariant only up to a certain phase, which cannot be cancelled by adding local counter term to the partition function. And when this is the case, you cannot consistently sum over background gauge fields. Hence, the anomaly can be viewed as an obstruction to gauging the symmetry. Let me make some remark on this. First, when G is finite, a background gauge field is dual to a network of topological defects implementing the symmetry, and background gauge field transformation are encoded in local remodification of these networks. And when you do this, in general, you can pick several phases. And this is what we can call a nomological viewpoint on anomalies that you might want to compare with the cohomological viewpoint that I gave you above. Also, before computing the anomaly, you really have to carefully specify what is the coupling of your theory to the background gauge fields. And in general, there might be different inequivalent couplings, which gives you different value of the anomaly. And a notable example of this is the so-called symmetry fractionalization, which can happen when your quantum field theory, together with the zero-form symmetry G, let's say, that you are discussing with background A, also has a generically higher form symmetry gamma with background that we will call B. And after you specify a reference coupling of all your symmetries to backgrounds, you can obtain a class of inequivalent couplings by formally shifting the background gauge field for the higher form symmetry by a term which depends on the background for the zero-form symmetry. And as has been emphasized in these two papers by last year, if there is also a pure anomaly for the higher form symmetry or a mixed anomaly between the zero form and the higher form symmetry, this shift can change the value of the anomaly. So this is possibly also relevant for the case of non-invertible symmetry that I will discuss. So it's something that you have to keep in mind, and it will come back at the end of the talk. Also, I define anomalies for invertible symmetry as obstruction to gauging. But there are at least three possible avatars of anomalies in this case. There are three equivalent facts. These anomalies can be also described as obstruction to realizing the symmetry in a trivially gapped phase, or also an obstruction to define a symmetric boundary condition, a boundary condition which preserves the symmetry. And these three equivalent facts tells you why we are so interested in anomalies. Anomalies are very useful since, obstruction to gauging and obstruction to defining symmetric boundary condition are interesting dynamical constraints. So anomalies can really constrain the dynamics of your quantum field theory. But on the other hand, anomalies are often quite computable. And this is related with the fact that anomaly can be defined as obstruction to gauging. Often this obstruction to gauging is very easily computable. And this gives you a good diagnostic tool for analyzing the dynamics of your quantum field theory. So what we want to do is to generalize anomalies to non-invertible symmetries, possibly preserving this nice property, okay? But in doing this, you must be very careful. Indeed, as has been emphasized recently by these authors, for non-invertible symmetry, these three things that I described are not really three aspects of the same thing. They are quite distinct concepts. They have relation among them that you can keep in mind. But in talking about anomalies, we have to choose one definition. And there might be, in principle, distinct concepts of anomalies. What I will use is that I will try to define anomalies as obstruction to gauging. And the reason why I'm going to do this is that I will show that, at least in the large class of examples they will discuss, which are the one of self-duality defects, anomalies with this definition turns out to be quite computable, but still they constrain the dynamics. Okay, but the reason why I put the word definition in quotes is that when you are dealing with non-invertible symmetry, the word gauging requires some caution. First of all, the cohomological viewpoint is not available since we don't know any concept of a background gauge field for non-invertible symmetry. We have an homological viewpoint, but this also requires some care. First of all, when you're discussing this homological viewpoint, you still have network of defects, but local remodification of the junctions, of the junction structure, are a bit more complicated, are described by these so-called F moves, which is a generalization of the picture that I show you above. And you have this kind of F symbols, which are kind of related with an anomaly, with an obstruction to gauging in the sense. But a crucial fact is that the non-triviality of these F symbols does not necessarily imply an obstruction to gauging. Indeed, a gauging for non-invertible symmetry is not defined abstractly, but it's subordinated to a choice of a certain object on your category describing the symmetry. It's called an algebra object. This is formally a sum of simple objects of your category symmetry, but it comes together with a choice of a morphism, which, roughly speaking, is a way to multiply this object by itself. And the gaugeability condition for the algebra is that quite schematically, the F symbols should be trivial on the algebra. So in the full category, the F symbol might be non-trivial, but it must be trivial when restricted to this algebra, and this is selected by the choice of this morphism. And more importantly, there can be actually various possible algebras. So there can be various possible gauging. So at this level, if I just tell you that an anomaly is an obstruction to gauging, this might be quite ambiguous. So the more precise definition that I'm going to use is that I will say that a non-invertible symmetry defect is anomalous if and only if there is no algebra which contains the defect. And the question I will try to answer is how to compute anomalies in this sense, and how to possibly incorporate also the symmetry fractionalization business in this setup. I have to tell you that in 2 dimensions, actually, many results about obstruction to gauging are already known, both in the mathematical literature and in the physical one. But going beyond 2 dimensions with this standard approach, with like mesh of defects and performing moves, could be quite complicated, is quite complicated. And so what I will try to do is to reformulate also the two-dimensional case in a different language using a different tool, which is the so-called symmetry topological quantum field theory. And I will show that many of the results obtained in 2 dimensions can be reobtained in this framework, and the generalization to higher dimension will be quite easy and straightforward. So, any question on this introduction? Okay, so let me review the basics of the symmetry TFT, the basic notion, which will be relevant for the discussion of anomalies.
There's actually a comment by Shuhang. Maybe Shuhang, you just unmute yourself and say it while in the chat. Sorry, I'm on trying. Okay. In 1 + 1, do you consider the I guess the Fibonacci diffusion category gaugeable? There's a Morita trivial algebra object containing the line.
I couldn't hear. Okay, I can see the comment in the chat.
So he's talking about the diffusion category with L squared is 1 + L.
Yeah, I see. Yeah, I consider the Fibonacci category gaugeable, and indeed this is what I was referring, that there is not a one-to-one correspondence between gaugeability and the fact that the category can be realized trivially. And indeed the Fibonacci category in some sense is anomalous in the sense that the Fibonacci line has non-integer quantum dimension, But yeah, indeed, you have to be careful when you discuss these anomalies in the sense of obstruction to gauging, since the consequence must be analyzed more carefully. Okay, should I go on? Okay, maybe we go on.
Yeah,
Okay,
sorry, you should go on. Yes, I thought you said thanks,
okay.
Shuhan.
Okay. So, what is the symmetry? As has been like be evident in the recent years, the symmetries in general of a d-dimensional quantum field theory are described by a fusion d-1 category. Let me call it C. And the symmetry GFT is a d+1 dimensional TQFT, which encodes all the data of your category. And what are the properties of this? Well, what you can do is to put the symmetry GFT in a slab with two boundaries. The left one encodes the local dynamics of your theory, so it supports a version of your quantum field theory where you are not taking care of the global properties of the theory. The global properties, on the other hand, are described by what happened on the other boundary, which is a topological boundary condition of your TQFT. And since the theory is topological, you can always shrink the slab and obtain back a d-dimensional theory. And the requirement is that there must be one topological boundary condition such that after this compactification, you get back your original theory with your original symmetry. But after you do this, what you can do is to keep fixed the local dynamics, keep fixed this left boundary, and start to changing and exploring all possible topological boundary conditions. So what you will get after this compactification are slightly different version of your original theory, in which the local dynamics is the same, but you are changing the global properties. And the symmetry category living on the boundary will be different and will be related from the original one by discrete gauging, or more generally, what I will call topological manipulations. And the correspondence is actually more precise. Indeed, there is a one-to-one correspondence between topological boundary condition of your symmetry TFT and this global variance. The global variance are all the slightly different version of your original theory, where you are keeping fixed the local dynamics, you are changing the global properties. But on the other hand, it is well known that there is also one-to-one correspondence between topological boundary condition of TQFTs and Lagrangian algebras of the TQFT. Let me explain what does it mean. A Lagrangian algebra, before he was describing what was an algebra, and here, by a Lagrangian algebra of a certain TQFT, I mean a certain algebra such that when you gauge it, you will completely trivialize the TQFT. This is because, very roughly speaking, the objects inside the algebra are mutually local. You can gauge the algebra, they do not braid among each other, but all the other objects in your TQFT braids non-trivially with the algebra. So when you gauge the algebra, you trivialize all the objects inside the algebra, but all the other will become not gauge invariant, and you have to throw them out. Okay, and so the correspondence between topological boundary condition and Lagrangian algebra is actually quite easy to understand. Indeed, you can cook up a situation in which you divide your space into two parts. In one part, you put your TQFT. In the other part, you put your TQFT where actually you gauge the Lagrangian algebra. So in this part, the TQFT becomes trivial, and so the interface between the two is actually a boundary condition. Alternatively, you can understand this boundary condition by allowing all the objects inside the Lagrangian algebra to consistently terminate on the boundary. And this tells you how the boundary category corresponding to this Lagrangian algebra is obtained. Indeed, when you allow all these objects in the Lagrangian algebra to terminate on the boundary, all the other objects are stuck, are confined to live on the boundary, and there they generate the boundary category. So this is how a certain Lagrangian algebra selects what is the global variant that you are going to consider on the boundary. So from this perspective, you should immediately understand what.
I think, or more of a comment, I think you have to be careful with Morita equivalence here. For example, in 3 dimensions, you can have fusion 2 categories that will arise from different Lagrangian algebras or different Lagrangian boundary conditions, but are not Morita equivalent. So these are not necessarily the same thing, I think. In 2 dimensions, that's okay, but
yeah, okay. Let me say this. In higher dimension, when the bulk is more than 3-dimensional, since on the boundary you can have several non-trivial TFT. Indeed, in drawing this diagram, you have to be a bit careful. There are some identification that you have to take. For instance, topological boundary conditions have to be considered by modding out the coupled TFT on the boundary. Is this what you meant?
Yeah, I mean, indeed, you can kind of, I mean, you can add a TQFT on the boundary that doesn't have a gapped boundary, and then it won't be Morita equivalent to the thing you started with.
I completely agree. Yeah, this is a bit sketchy, but by taking the right identification, this should be correct. Okay, so now you should immediately realize why the symmetry TFT is a useful tool to detect anomalies. Indeed, since I defined anomalies as obstruction to gauging a symmetry, and the gauging here are in one-to-one correspondence with Lagrangian algebras of your symmetry TFT, an anomaly is signaled by the absence of a certain Lagrangian algebra, which would correspond to gauging the symmetry. And I will be like more precise later on in saying what is the Lagrangian algebra you should look at, but this is the rough idea. Okay. Now, I have to tell you how to concretely construct the symmetry TFT starting from your original category. And a bit abstractly, what you want to do is to take your category living in the dimension, think about it as living in 1 dimension higher, and gauging it there. So in general, you cannot gauge in any dimension, but you can always gauge it in 1 dimension higher. More formally, this is what is known in mathematical literature as a state sum construction with input category C. But I want to be much more concrete and discuss the 2 examples that will be relevant for the rest of the talk. The first one is a theory with a zero-form symmetry given by a finite abelian group A with a certain anomaly. And so, as I told you, the first step is to take your symmetry, extend it 1 dimension higher. So what you will get is a trivial bulk theory with asymmetry given by a certain action. Is an SPT for A. And then you want to gauge the symmetry by making this gauge field dynamical. So the result will be a D+1 dimensional diagram Witten theory with a certain action omega. And it is well known, indeed, that the Dirichlet boundary condition for the gauge field lays on the boundary to your original group symmetry A with your original anomaly. But on the other hand, if the cocycle is non-trivial, there is no Neumann boundary condition that you can put, and this is the signal of the anomaly. Now, to discuss the more interesting and complicated example of the self-duality defect, I want to tell you about an extremely simple but actually useful idea in this step. That whenever you have a certain quantum field theory with a symmetry C, you can have a subcategory of your symmetry, let's say a set of defects which fuse consistently, and you may regard your theory to also have this subcategory C prime as symmetry. And you may care only about topological manipulation done using C prime only, and you will consider the symmetry TFT Z of C prime. This tells you that actually to any theory you can associate in general a hierarchy of symmetry TFT with increasingly larger symmetry categories. And since by considering topological manipulation of a smaller category, you will have less boundary, there should be a certain sense in which the topological boundary condition of a certain symmetry TFT are a subset of the topological boundary condition of the next one. This is not really precise. What is more precise, however, is that you can have a map from the Lagrangian algebra of a certain TFT, of a certain symmetry TFT, to the Lagrangian algebra of the next symmetry TFT. And this map can actually be described quite precisely in a situation which will be actually the relevant one in this talk, which is when, for going from one symmetry TFT to the next one, all the things that you have to do is to gauge a certain discrete symmetry, G. The important thing is that discrete gauging is always reversible. You can come back by gauging the dual symmetry, rep G. And so this map has a very precise description. Indeed, as I told you, a Lagrangian algebra is nothing but a way to trivialize the bulk with a certain gauging. So if you tell me how to trivialize the symmetry TFT for Cn, I can tell you how to trivialize the symmetry TFT for Cn plus 1. Indeed, I just have to concatenate the 2 operations on gauging first rep G, I come back to the previous symmetry TFT, and then I trivialize the bulk with the previous Lagrangian algebra. So this map induces a certain Lagrangian algebra L of n+1 from a Lagrangian algebra of the previous symmetry DFT. To not leave this discussion abstractly, and this is the example that I will discuss in the rest of the talk, let me talk about the duality defects, which are actually a non-trivial example of this setup. Duality defects arise whenever you have a d-dimensional theory where d is
There's a
even
question again from Shuang. He's asking whether
Yeah.
under this action, two boundary conditions can be identified on discrete gauging. And I think the answer is yes.
Sorry. Yeah, that's
Like
true.
in Tambay and
Indeed,
Dummies.
indeed, this is precisely why I was saying that this inclusion is not precise, because in general you would expect that you have less boundary condition, but some of them can be identified. So the more precise statement is that you have this map, and this map indeed is in general neither injective nor surjective. So let me go to the duality defects, which arise anytime you have a d-dimensional theory with d is even, let me call it 2n, which has a non-anomalous n-1 from symmetry given by a finite abelian groups. This is generated by certain topological defects of codimension n. And the theory is also required to have a self-duality under gauging this n-1 from symmetry. So you can convince yourself that the number are working well. This self-duality means that after you gauge this n-1 from symmetry, you will arrive in a theory which has a non-trivial isomorphism with your original theory. And this can happen in 2 dimensions with 0 from symmetry, and in 4 dimensions with 1 from symmetries. And 2 physical examples of this are in 2 dimensions, the Ising model, and in 4 dimensions, the n equal to first super Young-Mills theory at tau equals y. And the two dualities are respectively Kramers-Vanier duality and Montanari duality. And as has been shown in this paper by 2 years ago, when you have the self-duality, the theory, besides the invertible n-1 from symmetry, also has a codimension 1 topological defect n. And this is non-invertible, so since it has these peculiar future rules, in dimension greater than 2, what happens is that if you fuse the defect with its orientation reversal, you will get a condensation defect of the n-1 from symmetry, meaning that you are taking your n-1 from symmetry and you are condensing on a codimension 1 defect. And so this you get this future rule. The only exception is in 2 dimension. It's not really an exception. I mean, it's just a particular case, but in 2 dimension, everything is a topological line. And by fusing n with n bar, you will get a sum of lines of your 0 from symmetry. And it is known that in 2 dimension, the category that you get is the so-called Tambara-Yamagami fusion category. So you can immediately notice that this is actually an example of what I was describing before, because the category is made of your invertible symmetries and the non-invertible defects. So you can take a subcategory given by the n-1 from symmetry. Let me call it C0. And you can consider the symmetry DFT for C0 only, which is a simple Dijkgraaf-Witten theory for the abelian group A. This has this simple action is described in terms of 2 n-form gauge field. One is valued in the abelian group A, and one in its Pontryagin dual, namely its group of characters. This is a very well-known theory in d+1 dimension, and it has an n-form symmetry given by the product of these 2 abelian groups. And this is generated by dions, and which can braid in d+1 dimension. Notice that d+1 is 2n+1 here, and these are n-dimensional defects. So they have a canonical braiding, which turns out to be symmetric for n odd and antisymmetric for n even. But the important fact here is that since the two fields have the same degree, this theory also has a 0 from symmetry. Indeed, for any finite abelian group, its Pontryagin dual is dual to it, but it's not canonically dual. So to specify a symmetry, you have to specify explicitly an isomorphism for the group to the Pontryagin dual, and this in turn specifies for you a non-degenerate bicharacter, even by this formula. So this will be very important in this story. This choice will be the crucial one. And the claim that it's very simple to prove is that if this bicharacter is also symmetric, this induces a 0 from symmetry, which essentially exchanges the 2 sides. And it is because of this difference in the braiding, it turns out that the symmetry is Z2 for an odd and Z4 for an even. And these are, for example, the cases for 2 and 4 dimension. Indeed, this Z4 case reminds you about, for instance, the n equal to 4 super Young-Mills theory or Maxwell theory, which has this S-duality, which is G4. So, but, and okay, saying that this is the uniform symmetry means essentially that this symmetry is compatible with the braiding. So you just have to check this. It's very simple. The quite non-trivial claim, on the other hand, is that if you gauge this symmetry, what you get is the symmetry TFT for the full symmetry category, including the duality defect. And in doing this gauging, of course, you can also introduce discrete torsion given by a certain cocycle. In 2 dimensions, this is a sign, and it is known that it plays the role of the so-called Frobenius indicator on the boundary. And indeed, the boundary category is a Tambara-Yamagami category, and in the mathematical literature, this has been classified, and it is indeed known that they are classified by an abelian group, a symmetric bicharacter, and a sign, the Frobenius indicator. And now we are reproducing this known result from the perspective of the symmetry FT. And what we'll do is to propose that this is true even in higher dimension. We propose that in higher dimension, for instance, in d equal to 4, duality defects are still classified by this data. And epsilon can be regarded as an higher analog of the Frobenius indicator. And it turns out that this symmetric bicharacter and this epsilon are related with the F symbols, let's say in any dimension. The last thing that I have to tell you about the symmetry FT is how to obtain the duality defects on the boundary from the bulk. Indeed, as I told you, when you specify a certain Lagrangian algebra, the symmetry category on the boundary is obtained from the defects which breaks non-trivially with those in the Lagrangian algebra, and you stack them on the boundary. So you have to understand how the duality defect arise from the bulk to understand what kind of boundary condition you should look at to try to gauge the duality defect or detect its anomalies. And this is actually very simple. Indeed, before gauging G, this G symmetry will be implemented in the bulk by codimension 1 defects, and they have twisted sectors which are topological, and they are codimension 2. Let me call it sigma, this twist defects. But when you gauge the G symmetry, they become genuine codimension 2 defects in the bulk, and where they are stacked on the boundary because of the boundary conditions, they will become the duality defects. And this is important because this twist defect is characterized by the property that it's charged under the rep G symmetry. And so from this, you can understand what kind of boundary condition you should look at. Indeed, if you G was a zero form symmetry, so rep G is generated by topological lines. And if you allow, if your boundary conditions are such that these lines can terminate on the boundary, this corresponds to a Dirichlet boundary condition for the G gauge field. And in this case, the duality defect will be realized non-trivially on the boundary. And this is the boundary condition, which is essentially in the image of the map that was described before. It is already described by the symmetry DFT Z of C naught. On the other hand, you can try to put Neumann boundary condition for the G gauge field, and this will trivialize the duality defect on the boundary, meaning that you are gauging it. This will be not a boundary condition of the symmetry DFT Z of C naught. And the question we want to answer is whether this boundary condition exists or not. This will be our goal, given the data classifying the symmetry, to see whether the Neumann boundary condition is consistent or not. And the reason why this problem is accessible is that you can observe that since you can go from the symmetry DFT Z of C naught to the symmetry DFT Z of C by gauging G and rep G, you can move between these two symmetry DFTs. Even if this Neumann boundary condition is never a boundary condition of Z of C naught already knows if the Neumann boundary condition exists or not in Z of C. Okay. After you specify Z of C naught and how the symmetry acts on it, the symmetry DFT should know about it. And how does he know? Well, let us try to define a Neumann boundary condition for Z of C. Let's call it L. What you can try to do is to first gauge rep G. So you come back to the simpler symmetry DFT Z of C naught. and then you trivialize it by gauging a certain Lagrangian algebra L naught. And these two procedures, as I already told you before, trivialize the bulk theory, and so define a boundary condition on it. But this is not the boundary condition we are looking at. Since this is a Dirichlet boundary condition for the G-gauge field, we were looking for a Neumann one. So to define a Neumann boundary condition, we can try to gauge again G. We arrive in a pure gauge theory for G, and from this we can try to condense a magnetic algebra, namely putting Neumann boundary condition. You can see that this diagram is very schematic, and there are several operations which can be illegal. Indeed, we are trying to gauge G from the trivial theory, but this is not guaranteed to be possible. Indeed, this is a trivial theory, but must preserve the G symmetry to allow us to gauge to gauge G. So this is not completely a trivial theory; it must be a GSPT. And since we are obtaining this trivial theory by gauging L naught from Z of C naught, this gauging procedure should not break the G symmetry. Namely, this Lagrangian algebra must be G invariant. So this is the first punchline of this talk, is that you get this first obstruction to gauging the symmetry, to gauging the duality symmetry, saying that you can gauge it only if the Dijkgraaf-Witten theory, Z of C naught, admits a duality invariant Lagrangian algebra. And moreover, you can observe that the induced algebra from this the Lagrangian algebra, the boundary condition obtained by concatenating the gauging of rep G and LD, defines a boundary in which the duality defect becomes invertible. So this Lagrangian algebra exists only if the duality defect is a non-intrinsic, non-invertible symmetry. And so we can rephrase the first obstruction by saying that intrinsically non-invertible symmetries are always anomalous. And when this obstruction is not satisfied, either the non-invertible symmetry is spontaneously broken, or your theory must be gapless. So if you look for all possible Lagrangian algebras of this Dijkgraaf-Witten theory and there is no duality invariant ones, you can immediately give strong constraints on the dynamics. Okay. But this is not the end of the story. Indeed, now we can draw a more precise diagram, now that we know that after this Lagrangian algebra must be duality invariant. So when you gauge it, you will land on a SPT for G, and let me call Y the SPT phase for it. Then we gauge G with the discrete torsion epsilon, I remind you, the generalized analog of Robinet indicator. And the result of it will be a exists only if Y epsilon is trivial. So you get a second obstruction to gauging the symmetry, which is the triviality of this total twist Y epsilon. Okay, so what we did was essentially to split a full obstruction to having a Lagrangian algebra which gauges the defect into two obstructions which are simpler because are phrased in terms of a simpler symmetry GFT, which is a Dijkgraaf-Witten theory, is just C of C naught. So we can just look at this basic TGFT in D+1 dimension and see if these two obstructions are satisfied or not. If we can cancel both obstruction, then the duality defect can be gauged. Otherwise, there is an anomaly. And let me say that if the first obstruction is cancelled but the second is not, you can of course either break spontaneous symmetry, or in this case you can also realize the symmetry in a gapped but non-trivially gapped phase. So what I will do in the rest of the talk is to unpackage these two obstructions by finding explicit conditions on the data of your symmetry category, under which you have an anomaly or you can gauge the symmetry. So
again, Joanne has a question, and it's about sort of how general this is. Basically, it's in general difficult to classify all the gap boundaries. How do you know that there isn't actually an LD that does the job?
Yeah, I will.
Because
do
in
it
higher
in the
dimensions, you
rest.
don't really have an easy way to calculate all the Lagrangians.
Yeah, but we are considering just simple digraph Witten theories, and I will show that I can.
But I think you're
I can
probably
write down
assuming
all-
that all your Lagrangians descend from the Digraph-Witten theory, right?
Sorry, I haven't heard.
You're assuming that the Lagrangians come from
Yeah.
the Digraph-Witten theory.
Yes, yes.
It's not clear that
precisely.
the quotient theory doesn't have additional ones.
Yeah, okay. This was not really a rigorous argument. You can cook up a more rigorous one in the 2D, 3D setup. You can actually prove it that there are no
Sure,
further,
but there you have a
further
very
algebras.
rigorous criterion. I think
Yeah,
the question is about higher dimensions where you don't.
Yeah, in higher dimension, we essentially have an argument for this. You don't have really a proof because in higher dimension everything is much more hard to define. But still, okay, you have an argument which is quite convincing that all the Lagrangian algebras that defines a Neumann boundary condition must be of this form.
What's the argument? Basically,
I mean,
right?
it's a-
So in two
it's a
dimensions,
way to-
maybe just sort of in 2 dimensions, right? You have an algebraic condition and you just solve it, brute force, and that gives you all the Lagrangians. So what is your argument in higher dimensions?
Yeah, in higher dimension, it's kind of similar. It's kind of similar, but many things are not very precisely defined. So it's just an argument. It's a kind of making this what I said more precise. You can start from Z of C and try to directly go to a Digraph-Witten theory by gauging all the. Let's say we are in 5 dimensions. You can try to eliminate all the surfaces, and you can use the fact that if you assume that there is this Lagrangian algebra which gauges the duality defect, this Lagrangian algebra will be composed by both surfaces and the duality defect. But the point is that this Lagrangian algebra comes with a grading, which is given by rep G. So you can kind of argue that let's say the sub-algebra, this is not a precise notion I had mentioned, I have to say this, the sub-algebra made of the surfaces is indeed an algebra because it is the part of the algebra which has trivial grading. So you can kind of argue that you can still gauge it and you will remain with a Digraph-Witten theory for G. You can get rid of all surfaces by assuming that there is a Lagrangian algebra L. So it's the reversed argument that the one I told you before. But as I told you, in higher dimension, this is not a proof.
Yes, thanks.
Okay. So what I will do in the rest of the talk is to unpackage this 2 obstructions, and I will find explicit condition for gaugeability for the anomaly. So I will start from the first obstruction. So we just have to look for whether there is a duality invariant algebra of the Digraph-Witten theory. And let me start from the 2D 3D case. As I told you before, in 2D, in the 2-dimensional case, many of the results were already known by using categorical language. Here, it will reproduce the same results in this different approach, and you will see that the generalization to the 4-dimensional case will be incredibly easy. So it will be very quick at the end in the 4-dimension. There are very slightly different things. So here in 2D, it is pretty clear that topological manipulation of a 2-dimensional theory with a non-anomalous zero from symmetry A are classified by a subgroup of the symmetry that you want to gauge and a discrete torsion class. And it's a mathematical fact that all the information inside the class is contained in its associated alternating bicharacter, which is essentially its commutator. It's manifestly alternating and antisymmetric, and you can prove that it's actually a bicharacter. It's linear in both entries. So, and all the information, all the gauge invariant information on the class is contained in this kind of. I have to introduce a bit of notation before giving you the claims. But okay, you can introduce this subgroup of the punctuation dual, which is given by the subset of characters which annihilate all the elements of B. Then, using the fact that this chi nu is a bicharacter, I can define this psi nu, which is a group homomorphism from B to its punctuation dual, and is given by this formula. and then the rad nu is nothing but its kernel. Okay, this is not incredibly important, but this is a notation that useful to make this claim more concise. And the first claim is that, okay, as I told you before, you in general expect to have a correspondence between Lagrangian algebras and topological manipulations. So I have to tell you what is the Lagrangian algebra corresponding to the topological manipulation of gauging B with discrete torsion nu. And this is given by this very explicit subset. So it's not important that you follow all these formulas. I just want to make explicit. I just want to make clear that this is very explicit. You can write this this subgroup of A times A check, written in terms of B and psi nu, and you can prove all these claims are proved in the paper. The proof are sometimes quite technical, not incredibly illuminating, so I just give you the claims. Then you can prove that all the Lagrangian algebras of the Degrave-Witten theory are of this form. And moreover, the third and most important claim, once you have the form of all the possible Lagrangian algebra of Degrave-Witten theory, you can check whether there is at least one which is duality invariant, and the condition for the duality invariance is that you have to satisfy these two points. First, if you consider this isomorphism phi specifying the duality, the image of rad nu, which I remind you it's the kernel of this map psi nu, must be equal to NB, and moreover you can define this automorphism, which are required to be an involution. It must correspond to 1. So, okay, this might be not very illuminating, but now we discuss 2 examples. This is very explicit. If A is a cyclic group, of course, all subgroups are classified by divisors, and there is no discrete torsion that you can put since the second cohomology group is trivial. So rad nu is the full B, and you can check explicitly actually that all Lagrangian algebras are of this form. Let me take, without loss of generality, the symmetric bicharacter, namely the specification of the duality, to be of this simple form. And okay, you can apply the theorem above or check it explicitly that all Lagrangian algebra, the duality invariant condition is equivalent to say that P is equal to Q, namely N is a perfect square. So this means that whenever you have in this case we are in 2 dimensions, the category is a Tambara-Yamagami category. If it is associated to an abelian group, which is a cyclic group with N, which is not a perfect square, the duality defect will be automatically anomalous. And so whatever RG flow you will cook up with a relevant deformation which preserves the symmetry, it will end up in a phase which either spontaneously breaks the symmetry or is gapless. So this is very simple. A more interesting example is for A given by Zn times Zn, and let me assume for simplicity that N is prime. You can find example with N prime in the paper, but okay, let me assume it for simplicity. In this case, there are N plus 3 subgroups. The trivial one, which will not consider it. There are N plus 1 subgroups isomorphic to Zn. There is no discrete torsion for them. First, and there is the non-proper subgroup, which is of course not a subgroup, Zn times Zn, and this is the only one for which you can put discrete torsion, and this is classified by this N alternative bicharacter that you can write explicitly. There are 2 natural choices for the duality. This in principle is dictated by the boundary theory, but here we are just exploring all the possibilities. And you can write down the diagonal bicharacter of the off-diagonal one. And let me analyze both. First, for the off-diagonal, you can show that the first obstruction is always cancelled. Indeed, both the Zn subgroup generated by 1, 0 and the one generated by 0, 1 gives algebras, Lagrangian algebras of the bulk, which are duality invariant. And moreover, also the one associated to the ones, because there are many, one for each possible discrete torsion associated to the non-proper subgroup, you can write them explicitly. You can check that the duality invariant condition is equivalent to the fact that you can take R equal to, if R is plus or minus 1, this will be duality invariant. So by appropriately choosing the discrete torsion, you will get the duality invariant algebra. So in this case, with the off-diagonal bicharacter, the first obstruction is always vanishing. It's more interesting to look at the diagonal bicharacter. In this case, first you look for the Zn subgroups, and you see that the only one which can leads to a duality invariant algebra is the one generated by S, 1, with S which must be a quadratic residue of -1 mod n. And this does not always there is not always a quadratic residue of -1 mod n. And also, if you look at the non-proper subgroup, you will get the same condition, but for the number specifying the discrete torsion. Indeed, if you write down again the associated Lagrangian algebra and you look for the duality invariant condition, you will see that the number R specifying the discrete torsion must be a quadratic residue of -1 mod n. This does not always exist. For example, for n equal to 3, there is no such quadratic residue. Okay, let me now briefly discuss the 4D, 5D case, which, as you will see, is very similar because all we found can be easily generalized to the higher dimension case. Indeed, all the subgroups all the topological manipulation are still classified by a subgroup that you gauge and a discrete torsion class, which, however, now lives in a slightly different group, which is known to be the group of quadratic function over B. And of course, any quadratic function leads to a symmetric bicharacter with this standard formula, this standard polarization formula that you learn in linear algebra courses. And here, however, I will restrict myself to spin manifolds. Indeed, it is only in this case that this chi-nu, which is now a symmetric bicharacters, contain all the information on the discrete torsion class. And so the discussion will be pretty identical to the 2D, 3D case, just by replacing the alternating bicharacter with the symmetric one. Notice that here there are two symmetric bicharacters. One specifies the duality, and one is related with the discrete torsion. They play a completely different role. In particular, the one associated with the discrete torsion is not necessarily non-degenerate, but okay, they are both symmetric, so you have to keep in mind the distinction. And the claims are pretty the same as in the 2D, 3D case. You can see that the Lagrangian algebra associated to this topological manipulation is the same as before, that all Lagrangian algebras of this form. And also the claim about the duality invariance is pretty much the same. The only difference is that this automorphism, since now the symmetry is Z4, you can show that does not square to 1, it squares to -1. Not everything is essentially the same. And okay, a very simple example for a cyclic group with n a prime number, you will again get this condition that the first obstruction vanishes if and only if there is a quadratic residue of -1 mod n. So this is the case also in 4th dimension. And okay, you can find more complicated examples in the paper, but I will not discuss it here. So let me go to the second obstruction if there are no questions on the first one. Okay. Let me recall that the second obstruction was related with the possibility of having this total twist, which is vanishing. And I remind you that epsilon it's an SPT phase you put in the gauging, so it's a datum of your category. While Y is the SPT phase which arises when you start from your digraph Witten theory, Z of C naught, and you gauge this invariant algebra, which we are now assuming to exist. So we are now assuming that the first obstruction vanishes, and we are looking for the second one. So there is this duality invariant Lagrangian algebra. You gauge it, and you will arrive in a trivial theory which preserves the symmetry G. So generically, is an SPT for G, and I will denote this SPT phase by Y. So the question we want to ask is, where does Y come from? Because at this point, it's not totally clear why this Y is non-trivial or not. Why is there? And let's say the slope for it is that the point is this duality invariant Lagrangian algebra. I described it before just as a subset of the A times A check. I described it as a bunch of objects, but it's not only this. It also comes with morphisms, and you have to make consistent the presence morphism with the zero form symmetry G. Let me first consider the 2-3 decades, so the bulk is three-dimensional, as described by your friends. It's an MTC. So one important morphism that you have associated to this Lagrange algebra is a projection of the algebra onto all the objects contained in the algebra. So this is a local operator living on the line, which changes the Lagrangian algebra into the object inside the Lagrangian algebra. This is a local operator. And since this is a local operator, even if the Lagrangian algebra is invariant and can pass through the symmetry defect without any important difference, you can also discuss what happens to the local operator when it passes symmetry defect. And in general, you have to allow the possibility of having certain phases arising in this operation. These phases cannot be generic phases, and you can show that they are constrained by certain consistency equation. I will not write down the consistency equation. This is not terribly important for what I'm going to say. The only thing that you have to know is that there are these consistency equations, you can solve them. And in general, there might be several choices besides the trivial one. The trivial one is always possible, but in general, there can be other choices. So you have to make a choice of this. And this choice is what I would call a choice of equivariantization of the algebra. So this is a way to make consistent the presence of this duality invariant algebra with the presence of a zero from zero. The algebra as an object is invariant, but as a full algebra must be equivariantized. So you have to make this choice. And after you make this choice, you can actually, I will not explain the details, but you can actually really compute this phase. And this will be given by let's say, you have to take the sign of the sum of these phases. Here, I want to emphasize that the trivial choice is always possible. So if you come with a category with the forbidden zero indicator, which is trivial, if the first abstraction is cancelled, the second will be always cancelled, because you can always choose these phases to be trivial, and this SPTs Y will be trivial. But on the other hand, what I'm to say is that even for epsilon non-trivial, sometimes you will be able to find certain phases at a tilde, such that you will get an SPT phase Y, which is non-trivial and can cancel epsilon. So trivializing the second abstraction, even if epsilon is non-trivial. Okay. So now there are two questions that should come. First is how we can generalize what I told you to higher dimensions. What I told you was really based on the fact that we were with lines, and everything is quite, computable and tractable. We know how to define the morphisms on the lines. These are local operators. They pass through the defect. You can really be very excited and use the power of modular tensor categories to do this computation, which I'm not reviewing it, but trust me that it is hard to precisely generalize this choice of equivariantization to higher dimension and to this computation higher dimension. But this is a technical question. There is actually a much more physical question, which is how to interpret this choice of equivariantization from the boundary viewpoint. Because all I told you was that essentially was a trick that I'm describing everything with the symmetry TFT in the bulk of this duality invariant algebra. And I have this choice in gauging it. It seems a technical point. So why from the boundary viewpoint, I should have this various possible Y? So I'm gonna give you an answer which solves both questions. And the answer is that the choice of equivariantization in the bulk is nothing but a choice of symmetry fractionalization in the invertible boundary, namely the boundary in which the duality defects becomes an invertible symmetry. Let me explore carefully what do I mean. The point is that given this duality invariant algebra, as I told you, something that you can always do is to use an algebra in the symmetry TFT, including the duality defect, and this boundary condition where the duality defect becomes invertible. So it's a global variant which makes the duality symmetry a zero form invertible symmetry. And this symmetry, you can show that it always acts on the n-1 from symmetry. Into the dimension form a semi-direct product. dimension, they form a more complicated structure. It's a split to group. You can go even in a manner. But the important point is that this two symmetry turns out to have a mixed anomaly that you can compute explicitly. You can compute this mixed anomaly between the zero form symmetry G and the generically higher n-1 form symmetry A. And this mixed anomaly as a schematic form is quadratic in B in the background field for the n-1 form symmetry, and it's linear in A. The actual form is much more complicated, but I cannot tell you now here what is the form. It will take me at least half an hour. And the point is really related with the fact that the symmetry structure is a bit complicated. It is the semi-direct product or a split to group. But anyway, there is a precise form of the anomaly that you can write down, which is schematically is linear in A and quadratic in B. And you can compute it explicitly. It's always non-vanishing, So if you fractionalize zero form symmetry using this n-1 form symmetry by shifting the background gate field for the form symmetry with a term which depends on the background for the zero form symmetry, as I was telling you at the beginning, this shift formula is the pullback of a certain class called the symmetry fractionalization class. But the important thing is that you can realize immediately from this inflow action that if you put ink inside, you will change the pure anomaly for the zero form symmetry, for the G symmetry. You will get an extra term, which is a form. This is a pure anomaly. You are changing the pure anomaly with this shift. And the result that you can check is that this additional term is but Y. So this is the boundary counterpart of the procedure I described before. But you can realize that this is incredibly, it is much more simple than this complicated equivariantization procedure that you don't know even how to do it in dimension higher than 2. And so what you can do at this point is to compute it explicitly in many examples. And in 2 dimension, okay, I have to say that this proposal is very natural because this is a choice that you actually have on the boundary. And there was a choice in the bulk, so it's natural to match them. But then what you can do in 2 dimension, in which you, like both method, you can compute the answer with both method and check that they match. So you can do it in many examples, and you can convince yourself that this procedure done from the boundary viewpoint with symmetry fractionalization is precisely the boundary counterpart of the equivariantization procedure in the bulk. And then when you are convinced about this, you can use it to discuss the anomalies in 4 dimension, and you can compute it in many examples. I will not write on the, let's say, the numerology, because I don't think it's very illuminating here, but you can really be very explicit. This is much better than this complicated and hard to analyze procedure in the bulk. Here everything is very simple. You sit down, you solve a co-cycle condition in cohomology, you put everything into the file, you will get numbers from the result. You will see whether the second obstruction is vanishing or not. So I will summarize now. I discussed a possible definition for anomalies for an invertible symmetry. This is just one possible definition, which is useful, at least in this case. I mean, there can be various notions, but at obstruction to gauging in this setup of duality defect are computable, and they can imply non-trivial constraints on the dynamics. And indeed, you can see all these other paper of several colleagues of mine in which they put constraints on the dynamics on n equal to 1 star theories in 4 dimensions, which have flows which starting from n equal to 4 preserve the non-invertible symmetry. And using this result, you can give constraint to the dynamic. And of course, it would be very interesting to find other invertible symmetry preserving relevant information, both starting equal to 4 or in the many 2-dimensional conformal field theories which have self-duality defects in general. And one can use our result to make non-trivial prediction about the infrared phases of this flow, which are generally strongly coupled. I think it's also quite interesting to further analyze the relation between the obstruction to gauging and the obstruction to realize the symmetry in a trivially at mailing for dimension, maybe it's a good thing to analyze better. Another example, and also to study the implication of our result for the boundary conditions. An actually measured problem, I think that it would be interesting to analyze in the future, is the quantification of the obstructions. Because what I told you in all this talk was whether there was or there was not an obstruction to gauging. But for invertible symmetry, this is always quantified. And it is known that there are very well-known mathematical structures, which for bosonic systems are typically group cohomology groups, or more generic are coordinate group, which classify the obstruction. Is let's say the anomalous phase lives in a certain cohomology group. And this is due to the fact that for invertible symmetries, these obstructions have an additive structure. You can stack theory together, you can sum the anomaly, you can subtract the anomaly. So you have this algebraic structure which classify the anomalies. And at the moment, it is not known how to generalize this to non-invertible symmetry. We only know whether there is an obstruction either to gauging or to realize the symmetry in a trivially gapped phase, but it is not known whether we can really quantify this. And I think this is very important, because this gives you further constraints on the dynamics. Indeed, if I give you a certain theory with an non-invertible symmetry, and you come to me and you propose an effective field theory for the IR, we might agree that there is in both, for example, an obstruction to gauging. But if you quantify this obstruction, you can give further constraints, because also the value of the obstruction must be the same. But I think that in this moment, this is a problem which is quite hard to analyze with the present technology, and it's a problem for the future. So I think I will stop here.
Hey, thanks a lot. Are there more questions? Seems everything is clear. No further. We can also maybe switch off the recording and ask more questions then. Shall we do that, Apoorv? I will just stop it and then